Hi students, in this session I will discuss about signal bandwidth, system bandwidth and ideal filter characteristics. Okay, first I will start with signal bandwidth. Signal bandwidth. What is signal bandwidth? This we will see here. Okay, so to know the concept of signal bandwidth, first we will start with the spectral components of a signal. We all know that the spectral components of a signal extend from minus infinity to plus infinity. The spectral components, so that is in the frequency domain, the frequency components that is extended from minus infinity to plus infinity. The spectral components of a signal extend from minus infinity to plus infinity. We all know that. So any practical signal has finite energy. So if we see a practical signal, any signal, it will have a finite energy. So if it has an infinite energy, it will not stop anywhere. Okay, so signal will stop somewhere and it will have a finite energy. That is, any practical signal if you consider, it will have a finite energy. As a result, the spectral components approach zero as omega tends to infinity. That is, the value of omega tends to infinity, then the spectral components approach zero, because any practical signal has a finite energy. So we all know that the spectral components of a signal extend from minus infinity to infinity, and any practical signal will have finite energy. As a result, the spectral components approach zero as omega tends to infinity. If the omega value is going to infinity, then the spectral components will approach zero. So here, for that, we will neglect the spectral components having negligible energy. That is, the spectral components which are having very little amount of energy, we will neglect those and we will select only a band of frequency components having most of the signal energy. So in that signal, most of the energy is in a band of frequency components, and other band of frequency component, other free components will have a negligible energy. So that we will leave the spectral components having the negligible small amount of energy, and we will select only the band of frequencies components which are having most of the signal energy. So while transmission of a signal, some band of frequency components will have most of that signal energy, and the remaining frequency or the spectral components have negligible energy. So the spectral components which are having the negligible energy will be left, and we will select only a band of frequency components which are having most of the signal energy. And this band of frequencies that contain most of the signal energy is known as the bandwidth of the signal. So simply, the bandwidth of the signal is nothing but the band of frequencies that contain most of the signal energy. Simply, the band of frequencies that contain most of the signal energy is known as bandwidth of the signal. So while the transmission of a signal, most of the energy is located at a band of frequencies components. So that band of frequencies that contain most of the signal energy is known as the bandwidth of the signal. So this is simple explanation about signal bandwidth. Now we will see the system bandwidth. Here the first one. So system bandwidth. Okay, the constancy of the magnitude of transfer function in a system is usually specified by its bandwidth. So how the magnitude, that is the magnitude of the transfer function, is constant in a system, that will be specified by this bandwidth. Okay, we all know the transfer function. Transfer function. Okay, h of omega, that is nothing but y of omega by x of omega. So in that we are considering the magnitude. Okay, so the constant maintenance of the magnitude of the transfer function in a system is usually specified by its bandwidth. Simply, bandwidth, how we will define the bandwidth? The bandwidth of a system is defined as the range of frequencies. Over which the magnitude of the transfer function remains within 1 by root 2 times of its value at midband. of its value at midband, or within 3 dB of its value at midband. So if you go for with respect to decibels, then we go for 3 dB, okay? Or if you take generally, we will go for 1 by root 2 times of its value at midband, okay? Simple. The bandwidth of a system is defined as the, so the bandwidth of a system is defined as the range of frequencies over which the magnitude of the transfer function mod of h of omega remains within 1 by root 2 times of its value at midband. See the graph here, okay? So this is the graph for omega and magnitude of a transfer function, that is omega and mod of h of omega. The graph is like this, okay? Here the midband is this one, so this is the maximum band, midband is this one, so this is a midband value. So midband value I consider as A. I consider the midband value as A. So the bandwidth, how can I get the bandwidth? The bandwidth of a system is defined as the range of frequencies over which the magnitude mod of h of omega, the magnitude of the transfer function, that is the mod of h of omega, remains within 1 by root 2 times of the midband value. So here the midband value is A. So 1 by root 2 times 1 by root 2 into A. So there is a value. If A is 10, then I go for 1 by root 2 into 10. Okay, 1 by root 2, then 10 by root 2. I will get a value. So consider this value. So this is A. So A by root 2. Let us consider this one. Okay, there I will draw a straight line. It will cut the curve at 2 points. First point and second point. So extend the lines onto the omega at 2 points. Extend the lines from that point on omega axis. Extend the lines. So first one I will consider as omega 1 and the second one I consider as omega 2. Okay, starting one is omega 1 and last one is omega 2. Okay, so here in this graph, in the figure shown, the bandwidth of the system is nothing but omega 2 minus omega 1. That is higher cutoff frequency minus lower cutoff frequency. So this is the bandwidth. See, with this bandwidth, the value of this mod h of omega is within 1 by root 2 time of its midband value. So midband value is this one, that is 1 by root 2 time. So the graph is from this point to this point. See, almost it is constant and it is having the maximum value. So it is almost looking as constant. So it is 1 by root 2 time of its midband value. Okay. Simply, if you consider this in decibels, that is dBs. So this is a minus 3 dB of its maximum value, that is minus 3 dB of the value at the midband. Okay, if it is in decibels, we have to go for minus 3 dB. So maximum value minus 3 dB, and we have to draw a line and it will cut the curve at 2 points, extend those points onto the omega axis, then I will get the bandwidth in dBs. Okay, so here the bandwidth of the system whose mod of h of omega plot, that is whose magnitude of the transfer function plot is shown in the figure, is omega 2 minus omega 1. This omega 2 minus omega 1 is the bandwidth. Simply we will represent this as bandwidth, where omega 2 is the upper cutoff frequency or upper 3 dB frequency. It is in 3 dBs, then we call what is upper 3 dB frequency, or we can call it as upper half power frequency. Upper half power frequency, omega 2. In the same way, omega 1, lower cutoff frequency, lower cutoff, because lower frequency got lower cut, it is lower frequency, it is lower cutoff frequency, and lower 3 dB frequency, or it will be called as lower 3 dB frequency or lower half power frequency. Here omega 2 is the upper cutoff frequency or upper 3 dB frequency or upper half power frequency, and omega 1 is the lower cutoff frequency, lower 3 dB frequency or lower half power frequency. And this is simply regarding the system bandwidth. Simply, the bandwidth of the system is defined as a range of frequencies over which the magnitude h of omega remains within the 1 by root 2 times of its value at midband, or within 3 dB of its value at midband. Simple. Okay, so it's nothing but the range of frequencies over which it is almost constant. See here, that is almost looking constant. Okay, the graph will be constant. Now see the last point, that is the band limited signals can be transmitted without distortion. The band limited signal, that is the band limited signals can be transmitted without distortion if the system bandwidth is at least equal to the signal bandwidth. If the system bandwidth is at least equal to the signal bandwidth, then the band limited signals can be transmitted without distortion. So for the distortionless transmission, the system bandwidth is at least equal to the signal bandwidth. So this is the our relation for system bandwidth and signal bandwidth for distortionless transmission. Okay, so the band limited signal can be transmitted without distortion. That is, for distortionless transmission, the system bandwidth is at least equal to the signal bandwidth. Okay, so this is explanation regarding signal bandwidth and then system bandwidth, and how the signal bandwidth and system bandwidth are related for distortionless transmission. So simple for distortionless transmission, that is, the band limited signals can be transmitted without distortion. That is, for distortionless transmission, the system bandwidth is at least equal to the signal bandwidth. Okay, now we will move on to the next topic, that is ideal filter characteristics. Now we will discuss about the topic ideal filter characteristics. Now we will discuss about the topic ideal filter characteristics. We all know a filter is a frequency selective network. That is, it will allow a signal transmission for a particular band of frequencies and it will attenuate some other frequency band. Okay, so we all know this. We all know about the filters. So we all know different types of filters: low pass filter, high pass filter, band pass filter, and band reject filter. Now we will see the ideal filter characteristics. Ideal, perfect. So if it want to stop, it will stop exactly. If it want to pass, it will pass the complete signal. So ideal means exactly, perfectly. Okay. Now we will move on to an ideal filter. An ideal filter has very sharp cutoff frequency. An ideal filter has very sharp cutoff characteristics. Simple. An ideal filter has very sharp cutoff characteristics. Cutoff characteristics means if it has to stop the signal, it will stop it exactly, perfectly. Okay, very sharp cutoff characteristics. And if you want to pass up to that frequency, it will pass all the signals up to that frequency, and it will stop the signal after that frequency. It is very, very sharp cutoff frequencies, and it passes signals of certain specified band of frequencies. So the ideal filter passes signals of certain specified band of frequency exactly, perfectly, and totally rejects the signals of frequencies outside this band. So this ideal filter passes the signals of certain specified band of frequencies exactly or perfectly, and it will totally reject the signals of frequencies outside this band. It will totally reject. Okay, its phase spectrum is linear. This ideal filter characteristic phase spectrum is linear. Okay, now we will see the ideal versions of different filters. And their magnitude responses as shown below. Okay, now we will see the ideal versions of different filters. So we have different filters. For all those filters, we will see the ideal versions and their magnitude responses. So we have the different filters, like I already told you: a low pass filter, high pass filter, band pass filter, band rejection filter. Along with this, there is another filter, and this is all pass filter. Okay, now we will see this ideal versions. Okay, first I will start with the ideal low pass filter. Ideal low pass filter. So low pass filter will allow the low frequency signals. Okay, will allow the low frequency signals. It has a sharp cutoff frequency. Inside that cutoff frequency, all the signals will be allowed. So after that cutoff frequency, no signal will be allowed. That is, the signals will be attenuated after the cutoff frequency. That is, totally rejects the signals greater than the cutoff frequency. Okay, so this low pass filter will totally rejects the signals which are having greater than the cutoff frequency. Okay, that is, see here I had down the graph. Okay, for omega versus mod of h of omega, that is frequency versus transfer function. Okay, magnitude of the transfer function omega and h of omega. Okay, here it will ideal low pass filter. That is, here there is a term omega c, which is nothing but cutoff frequency. That is, it will allow all the signals having the frequencies between minus omega c and plus omega c. Between these values, it will allow the components of all frequency components. So it will allow the signal between the frequencies minus omega c and plus omega c, and it will totally reject the signals having the frequency greater than omega c. Okay, so outside of this omega c and minus omega c, outside of this band, this ideal low pass filter will reject total signals which are outside of this band. So inside this band, that is between minus omega c and omega c only, it will allow the signals to pass through them. Okay, so this will be represented as C. Here I taken the magnitude as 1. So mod of h of omega, that is magnitude of the transfer function, mod of h of omega equal to 1 for mod of omega is less than omega c. That means minus omega c less than or equal to omega less than or equal to plus omega c. But between this range, the value is 1. And the value of mod of h of omega equal to 0 for mod of omega greater than omega c. That is after this omega c and before this minus omega c. So here and here. For all these, the value of mod of h of omega equal to 0. So we can represent this, the ideal low pass filter can be specified by the equation, this one. Okay, first one. In the same way, come to the ideal high pass filter, simple high pass filter. So it will pass only the high frequency signals. Okay, high frequency signals. And there also there is a cutoff frequency omega c. So they will allow the signals having the frequencies greater than omega c and less than omega c, they will totally reject. See, as shown in the figure, here also I had drawn the graph for omega and mod of h of omega. Mod of h of omega, that is magnitude of the transfer function. So if you draw the graph for this one, see this is the magnitude 1. Magnitude 1. So here is 1. Magnitude 1. Now omega c is the cutoff frequency. Now this is minus omega c. Now this ideal high pass filter will allow the signals which are greater than omega c, after omega c and before minus omega c. So outside of this, they will allow all the signals. So I represented that one with like this. Okay, for the different color. And it will totally stops the signal passes of frequencies less than omega, between minus omega c and plus omega c. So between minus omega c and plus omega c, it will not allow the signals to cross to this. So the signals having the frequencies between minus omega c and plus omega c are not allowed to pass through the system for an ideal high pass filter. Okay, so simply the ideal high pass filter can be specified by mod of h of omega will be equal to c 0 between minus omega c to plus omega c. It is 0 for mod omega is less than omega c. So between this, and this value is equal to 1 after omega c and before minus omega c. That is 1 for mod omega c greater than omega c. For this value will be equal to 1. This is ideal high pass filter. Now coming to the ideal band pass filter. Ideal band pass filter. So the name band pass filter, it will allow only the band of signals. Okay, a particular band of signals. So I am considering the band as omega 1 and omega 2. So there are two frequencies, omega 1 and omega 2. In between that omega 1 and omega 2 only, the signals will be allowed by this band pass filters. In the same way, between minus omega 2 and minus omega 1, between these only it will allow. That means that this indicates a passage of the signal. So here the signal will flow through the system having the frequencies between omega 1 and omega 2, or simply if the omega value should be between mod of omega 1 and mod of omega 2. If it is between these two, for that frequencies the signal will be passed. And for all other remaining frequencies, that is from minus omega 1 to plus omega 1 and greater than omega 2 and before minus omega 2, all other frequencies, the signal will be completely stopped or rejected. Okay, so it will pass only the band of signals, that is in between mod of omega 1 less than omega less than mod of omega, that is between this and this. This band only it will allow the signal passes. For all remaining frequencies it will reject. Hence we can specify this ideal wave band pass filter with mod of h of omega equal to 1 for mod of omega 1 plus or minus less than omega less than mod of omega 2. That means only between this, between minus omega 2 to minus omega 1 and between omega 1 to omega 2, the signal will pass with only that frequency band. For all other remaining frequencies, the signal is completely rejected because it has a very sharp cut of characteristics. That means after that it will be stopped. It will allow only this band of frequencies. Okay, so this is how we will specify the ideal band pass filter with the equations. And next one, ideal band rejection filters. Okay, so band rejection filters, that means it will reject in a particular band. Consider same band, omega 2 and omega 1. So here omega 1 and omega 2. Between this band, it will reject all the signals. In that band of frequencies, it will reject all the signals. That is between minus omega 2 to minus omega 1, all the signals will be rejected. And between omega 1 to omega 2, all the signals will be rejected. In the last case, in these frequencies, the signal is passed. But here, the signal is totally rejected in the frequencies minus omega 2 to minus omega 1 and omega 1 to omega 1. Omega 1 to omega 2, and in all other remaining cases the signal will be passed, because it will reject only this band of frequencies. For all other remaining frequencies, the signal will be passed. Hence, the signal is passed. This is for passing. Omega minus omega 1 to plus omega 1, the signal will be passed, and greater than omega 2 it will be passed, and before minus omega 2 it will be passed. For all here it will get passed. So band pass filter or band reject filter. For band pass filter, only the signal will pass only in the band of frequencies, but for band reject filter, the signal will be rejected in the band of frequencies. This is the only difference between band pass and band reject. That is completely opposite. These two are opposite to each other. Okay, band reject filter. Okay, and this band reject filter is specified by mod of h of omega equal to 0, where here between these two 0, mod of omega 1 less than mod of omega 2, and it will be equal to 1. It will be equal to 1 for omega less than mod of omega 1. Omega less than mod of omega, between this one, this is 1, and omega greater than mod of omega 2. Mod of omega 2 means this one and this one. So in these two cases it is 1, and in this case also it is 1. So I will represent this with this one. Okay, so there is 1 for omega less than mod of omega 1 and omega greater than mod of omega 2. See here, this dotted line for all these filters, that is for low pass filter, for high pass filter, for band pass filter and band reject filter, this will give the phase. This is a linear phase, linearly varying, theta of omega, linear phase, theta of omega. This is theta. So that is for this the phase function for the distortionless transmission is minus omega td, Okay, the corresponding phase function for the distortionless transmission is minus omega td. Clear? And the last one is all pass filter. All pass filters, simply all pass. So it will pass the signal with all frequencies. Okay, so all the frequencies, right from minus plus into all frequency, it will pass all frequency, and hence it is an all pass filter. Okay, all pass filter. So omega, h of omega, and beta of omega. Just the signals having all frequencies will be passed through these systems. There is no rejection. It will pass it will allow the signal with all frequencies. That is all pass filter. Okay, simply that will be represented with this diagram. Mainly we need these four. That is ideal low pass filter, ideal high pass filter, ideal band pass filter, and ideal band reject filter. Okay, and these are specified with these equations. And this is nothing but linear phase, theta of omega, and for all these the corresponding phase function for distortionless transmission. Phase function for distortional transmission is minus omega td. Here for this the phase function for the distortional transmission is minus omega td, and it is linear. Okay, so here this ideal low pass filter, ideal high pass filter, ideal band pass and reject filter will pass the signal without distortion. All this will pass the signal without distortion. Without distortion, they will allow the signals. Hence, it is ideal low pass, ideal high pass, ideal band pass, and ideal reject filters. All ideal filters are non-causal systems. These all ideal filters are non-causal. Okay, non-causal system. Hence, none of them is physically realizable. We can't realize them physically because they are non-causal systems. Okay, only causal systems are physically realizable. But if all ideal filters are non-causal system. Hence, none of them are physically realizable. We can't physically realize those filters because these are all non-causal systems. Okay, so this is the explanation about ideal filter characteristics. Okay, mainly we have four types of ideal filters, that is ideal low pass filter, ideal high pass filter, ideal band pass filter, and ideal band reject filters. Along with this there is one more one, that is all pass filter. Okay, so I shown the waveform representations and equations, okay, for all these waveforms. So I hope you are all clear with this ideal filter characteristics. Okay, now we move on to the next topic. Now we will move on to the topic causality and polyvenier criterion for physical realization. Okay, causality and polyvenier criterion for physical realization. Okay, so here we know for an LTI system to be causal, the condition is, we all know the for an LTI system to be causal, the condition is h of t equal to 0 for t less than 0. So that is we all know. Now physical realizability implies that it is physically possible to construct that system in real time. Physical reliability. So we have to construct that system physically, that should be possible in real time. Then we can call that as a physical reliability. So physical reliability implies it is physically possible to construct that system in real time. So we have to construct the system in real time. So if it is physically possible to construct the system in real time, then we can call that as a physically reliability. Now, a physically reliable system cannot have a response before the signal is applied. Very, very important. A physically reliable system cannot have a response, that is, the physically realizable system does not have an output, response output, before the signal is applied. So that is before the input is applied. So it does not have the output before the input is applied. That is, a physically reliable system only have the generate the output only after the input is applied. So a physically reliable system cannot have a response before the signal is applied. This is known as causality conditions. We all know that this is the causality condition. The causal condition is the system has to produce the response only after the signal is applied. That is, it cannot have a response, the system cannot have a response before the signal is applied. That is known as a causality condition. So that is h of t, that is an impulse response. Impulse response of a physically reliable system must be causal. Must be causal. That is h of t, the impulse response of a physically realizable system must be causal. Okay. So all this is in time domain criterion of physical reliability. So I explained all this. This is the time domain criterion of physical reliability. So I explained everything in terms of the time domain. Now we will go for frequency domain. How the changes will occur, see. We will see. In frequency domain, the condition for the magnitude function, that is the magnitude of a transfer function h of omega, the condition for a magnitude function h of omega to be physically realizable is, so before this I explained everything with respect to the time domain. Now in frequency domain, the condition for the magnitude function h of omega to be physically realizable, that is h of omega has to be physically realizable. The condition is integral minus infinity to infinity ln of mod of h of omega by 1 plus omega square d omega is a finite value, that is the value is less than infinity. Integral minus infinity to infinity ln of mod of h of omega by 1 plus omega square d omega, this value should be a finite value, that is this value should be less than infinity. So the condition is this one. So in time domain, the impulse function h of t of a physical reliable system must be causal, but in frequency domain the condition is the magnitude function h of omega to be physically reliable is integral minus infinity ln of mod of h of omega by 1 plus omega square d omega is less than infinity. Now the magnitude function mod of h of omega, the magnitude function mod of h of omega must however be square integral before the polyvariant criterion is valid. So before valuing the polyvariant criterion, we have to square the integrable. Okay, square the integrable, that is square integral minus infinity to infinity the magnitude of the transfer function mod of h of omega square d omega we have to consider before the polyvariant criterion. Okay, the magnitude function mod of h of omega must however be square integrable before the polyvariant criterion is valid. Before the polyvariant criterion is valid, that is integral minus infinity mod of h of omega square d omega should be less than infinity. So that square integral before the polyvariant criterion is valid. We have to go for that one. And finally, a system whose magnitude function violates the polyvariant criteria has non-causal impulse response. So if there is a system having the magnitude function which violates the polyvariant criteria, has a non-causal impulse response. Non-causal impulse response, that is simply the response exists prior to the application of driving function, that is the output will be available before the input is applied. Simply the response exists prior to the application of the driving function. So before applying the driving function, we will get the response. So this is nothing but the non-causal impulse response. So a system whose magnitude function violates this polyvariant criteria has non-causal impulse response. That will have a non-causal impulse response. Non-causal impulse response means that the response exists prior to the application of driving function. Actually, so here the response, there should be no response before the signal is applied. That is, the response should be after the signal is applied. But for non-causal impulse response, the response exists prior to the application of the driving function. This is for the systems whose magnitude function violates the polyvariant criteria. If it follows the polyvariant criteria, then the response will be after the signal is applied. That is, we cannot have a response before the signal is applied. Okay, so I will conclude. The conclusions of this one is First one, ideal filters are not physically realizable. Ideal filters are not physically realizable. The first one. Next one, a realizable magnitude characteristic cannot have too great a total attenuation. The last one is a realizable magnitude characteristics cannot have too great total attenuation. Too great total, it cannot have a total attenuation of too great. Okay, a realizable magnitude characteristics cannot have a too great total attenuation. So these are the two conclusions that I can derive from this polyvariant criteria. Okay, so this is the explanation about causality and polyvariant criterion for physical realization. So simply the physical realization implies that we have to physically, it is physically possible to construct that system in real time. So in real time we have to construct the system physically, that is a physical realization. So for that we use causality and polyvariant criteria. So I explained everything about the causality, and first I explained about the causality, and then I explained about physical realization, and then I gone for the polyvariant criteria, both in time domain and then in frequency domain. I given the equations for the frequency domain. Okay, and finally I go for the two conclusions of this polyvariant criteria. So this is the explanation about causality and polyvariant criteria for physical realization. So after this we have one more topic, that is relation between bandwidth and rise time. Okay, bandwidth and rise time. So you all know the transfer function of a low pass filter, h of omega. So using the transfer function of a low pass filter, the equation for h of omega, you can calculate the relation between bandwidth and rise time. Okay, now I am giving this as practice for your work. That is, you have to derive the relation between rise time and bandwidth. That is, you have to derive the relation between bandwidth and rise time using the transfer function of a low pass filter. Okay, this is for your work. Okay, so with this I am finishing today's class. Okay, thank you one and all.